All right, hello everybody. My name is Robin Grindley. I'm a Principal Product Line Manager for the core switch group at Broadcom. You know, Broadcom, it gets bigger and bigger and bigger every day. We're one of the business units that does the big Ethernet switches that typically go into cloud and enterprise segments. So today I'm going to be talking about a brand new chip. It's just started sampling called Trident5-X12. And the premise I'm going to try and convince you of is that the cloud infrastructure needs an upgrade, and we hope that Trident 5 is going to be an essential ingredient in that upgrade. Okay, so just quickly about Broadcom and our switching portfolio. We have three basic product lines, all focused on different market segments. On the enterprise segment, and this is mostly enterprise data center, but also touches some of the cloud, which we're going to touch on today, is the Trident line. For the real hyperscalers, just the maximum speeds and feeds that you can cram into a piece of silicon on a reticle, there's the Tomahawk. And then we have a Jericho, used to be the Dune or DNX line, and that is focused on maximum capabilities and scalability, looking at service provider markets. Now, we have these three product lines. They're very different market segments. There's a lot of overlap. You will see any of these chips can sometimes mix into the other ones. Tomahawk will get used in enterprise. Trident will get used in the cloud. The Jericho will get used in all sorts of different edge applications, cloud, you name it. So while we have the three product lines, they have different capabilities, and every customer, the key is that every customer gets to pick within that product line and between the product lines and figure out exactly what they want. We have all of the bases covered. So it's in the name, Broadcom, right? We try and cover everything. All of these families, they use one API. So from an OEM who's developing these boxes, whichever one of these chips they buy, they develop the same software to manage those boxes. So while we have a broad portfolio of products, we make them as common as possible for the users, cloud operators, and everybody, all the way up to the top. So we want to make a consistent look and feel, even though there's a lot of different capabilities under the hood. So in today's talk, I'm the first presenter. There will be three. I will be talking about Trident5-X12, and then we're going to have another presenter on Qumran 3D. That's in the Jericho line. And then another presenter, our final one, will be talking about Thor 2, which is a new NIC device that has been added into our portfolio. And again, if there are any questions at any point, feel free to jump in. So the Tomahawk and Trident line together form a sort of subfamily that we call XGS. And this is mostly a historical precedent of how we came into the company. The XGS line was kind of the original one, then we acquired Dune and brought in this Jericho line. So XGS is Tomahawk and Trident together. And there are many family members shown in the slide. For Trident, we go back probably 20 years. So the Trident line is now on its 5th generation. And every generation adds features and functionality, but we have to keep legacy compatibility. Everybody who's been using our chips expects that it can do everything it used to do, but it can do new stuff as well. So part of the complexity in developing all of these chips is to make sure that you don't break what's already working, right? Customers only want improvements as they go along. So I've actually got, unfortunately, if you're remote, you're not going to be able to touch and feel these, but I've got the three generations that almost are shown here. Off the slide, earlier than 2018, there was a Trident 3 family. And this is a programmable, fully programmable data plane chip that goes up to 3.2 terabits per second. So this was our first Trident that was programmable. You can pass these around. They are mechanical samples. You can't break them, and you can't sell them either. I mean, you could try, but. The next one is this Trident 4, one member of the Trident 4 family. And that's actually the TD4X7 that's shown in the lower right-hand corner. This is a brand new 4 terabit chip, also fully programmable, compiler programmable. It uses programming language that we call NPL. We'll discuss that a little bit more in the context of TD5. So that's a Trident 4 generation. And the Trident 4 generation, that one supports 50 gig PAM4 SerDes, which means it supports 200 gig and 400 gig ports. Then we come to the latest generation. So these are Trident 5s, the Trident5-X12 that we're discussing today. So these support 100 gig PAM4 SerDes, meaning they can go up to 800 gig ports. And we will see as we go through the presentation, that's kind of where a lot of the servers are headed in the next generation, particularly in the AI/ML space. You will notice that this one looks different than the other ones. So this is a trend right now with larger and larger packages with power that's getting hit with these chips. This is a lidless package. So the other packages, you just see a metal lid over top. It's the same die underneath, but we put it in a compound and then glue on a metal cap to it. For thermal reasons, that has a thermal resistance, makes it a little more challenging to cool. So nowadays, the trend is to go lidless. So this is the actual die, and then whoever manufactures the box will put the heatsink directly on the die itself. So less thermal resistance, better overall thermals. So again, you can pass those around.
So this would be the lidless die.
That's a lidless package. The die is the thing in the middle, the silver thing in the middle, and then there's a substrate, which is that green thing, which is like a small printed circuit board.
Awesome.
And then on the bottom, they have to put on the balls. This one, although it looks daunting, is actually a small number of balls. It's only about 2,000. Some of the latest chips are getting up to around 8,000 balls on the bottom of that package.
I love this.
So imagine trying to solder that down to a PCB.
Me too.
No.
Can be challenging. So Trident 5-X12 is out. It's sampling now. Boxes with this chip in it should start being available probably in about 2 months from certain OEMs.
Don't you have 100 gig already out though?
Yes.
That's
yeah.
not Trident though. What is it then?
Tomahawk. So this Tomahawk 5, the 51.2 tera, has 100 gig PAM4 in it. As does the Tomahawk 4 generation before it. We have two versions. We have 25.6T in Tomahawk 4. One version has 50 gig PAM4, another version has 100 gig PAM4.
Okay, is Dell and their servers doing Tomahawk, or are they doing?
I think they use all of our chips in different product lines. All three of the
all three of them are going into their
Jericho, Trident,
servers?
and Tomahawk in
Okay.
various different products. So the Tomahawk would typically be in the spine or fabric of a cloud, right? Hooking everything together at the top. The Tridents usually are at the top of rack, servers down, and then up to the spine and fabric or the leaf on the northbound interface.
Okay.
And then often the Jerichos are at the DCI, data center interconnect. So when it goes outside of the data center and you need huge route scale,
Okay.
that's typically what, so usually different boxes in one data center, you'll see all three of these product lines. But as I said, they kind of can mix. You can see Tomahawks as top of rack. You can see Tridents being used in enterprise as spine and fabric chips. So every customer kind of picks their own.
Before you leave that slide, there's a lot of numbers on there, and I know what some of them probably mean.
Good question.
Sure.
Just to help explain it a little bit for me, because I'm not a networking person necessarily. So I see 512 by 100 gig PAM4. Can you dissect that a little bit for me? What's the 512? What's the 100 gig and the PAM4?
So each ball on the SerDes, actually it's two balls, but is a SerDes. So it's a single high-speed serial connect. Okay. 50 gig PAM4 means that the rate coming out of that ball on the package is 50 gigabits per second.
Okay.
Per lane. So think of one lane of a SerDes. Now, that one lane of a SerDes could connect to an SFP, like one-to-one. And then it goes to optics, and then that's your, say, a 50 gig SFP, single module, optical module.
Okay.
You could gang four of them together, 450 gig SerDes together make a 200 gig MAC. So that's a 200 gig port. Or you could put 8 by 50 gig, and so on the front panel, if you have an OSFP, it's typically going to be a 400 gig or an 800 gig, and it's consisting of 8 lanes of SerDes. If they're at 50 gig, the 8 by 50 is a 400 gig OSFP module.
Okay.
If they're running at the latest 100 gig PAM4 on each SerDes lane, times 8, that's an 800 gig optics module.
Okay.
So it's the SerDes rate. PAM4 is a modulation. I mean, that's just, that's down in the weeds of how you get signals across this thing at this higher rate.
Okay.
Right? But pulse amplitude modulation. And then that's the number of SerDes that are at that rate on the chip.
So
256 SerDes, all of them capable of 50 gigs each.
okay.
And that gives you the 50 gig PAM4 has 512 SerDes times 50 gig, which gives you the full 25.6 terabits per second of overall throughput on the entire chip.
Okay, so you can take those lanes and combine them together as needed to create a 100 gig, 200 gig, 400 gig connection.
You can you can flip around on the fly these SerDes to be whatever you want. Like a single lane is just 100 gig coming out to an SFP, or 8 of them is an 800 gig port, or 4 of them, or 2 of them. Yeah.
And that's a determination that the OEM makes when they're putting your chip in their device?
Usually, no. The OEM builds it into the box, and what you can do is you can still change it on the fly. So if you have an OSFP cage on the box, right, you can plug in an 800 gig OSFP, and then it's a single 800 gig port. You can plug in a breakout module, which is still an OSFP, but it comes out with 4 pigtails, which goes to 4 by 200 gig each. And so you could make it, so you can still physically do it. And the OEM, the operator goes in the software and says, reconfigure this port as 4 by 200 instead of 1 by 800. And then plug in the appropriate, you have to get, somebody to go in there and stick in the appropriate breakout module.
Right.
And you can have any port combination you want.
Cool. Thank you.
So it's completely flexible.
Yeah.
Anything else on
Robin,
this slide?
this is Ron.
Yep.
Jumping in remotely. This is very helpful. And I was just curious about the 425 gig Ethernet ports. I'm deducing that's related to management applications.
Yeah. Typically, I'll show you on the next slide a block diagram of the chip. These are all front panel, like that would come out to front panel. There's a separate management port on all of our chips. Usually it's a 4 by 10 gig or a 4 by 25 gig, but that is separate. It's still available, and it still can feed traffic to and from the front panel ports. So it's kind of off to the side, but it's lower speed. And it's a different type of SerDes, lower rate. So we don't, it's not in the headline, so it's actually 25.6T plus a little bit with the management port.
Got it. Very helpful.
Okay. So context, why do we need to make cloud networking better? Well, because the world is changing. You've probably heard of AI/ML. It's thrown the apple cart over. Everything is changing. We're all trying to figure out how do we address this new networking infrastructure. The CPU and compute infrastructure and cloud, that's been going for decades, and we know that pretty well, although there's still a lot of, as we scale up, there's still challenges with traffic engineering, security, et cetera. You add AI/ML into the mix, and it just exacerbates everything. Now we have a front-end network, which is to your CPU servers. You have a back-end network that's going to all of your GPU servers, and you're trying to eke out all the performance you can get within a certain power budget. So the problem statement has just gotten an order of magnitude bigger. And the approach to saying, okay, we can try and do new things, new traffic engineering, new telemetry, new something. If you try and do this in software, if you have software in the loop, even if it's an embedded software running on the chip, it's too slow. You're dealing with 16 terabits per second in this chip. We have 51 terabits per second running through our Tomahawk 5s. You can't do anything with software. It all has to be in hardware. It has to be running at line rate. So whatever you're going to do, you need to be able to do it at line rate in the hardware. And that applies to performance. So obviously, tail latency is the main metric, job completion time, when you're running AI/ML workloads. But congestion control, as these networks scale up, and particularly with the new traffic patterns that AI/ML brings with it. It's not sort of the standard everybody going everywhere. It goes in phases, right? When you're doing training, it goes in a big phase of data out, everybody computes, and then they all synchronize, do a barrier, come back in, and it's like kind of breathes over and over again. The traffic is very, very different in an AI/ML network than it is in a compute network.
In the last 12 months has just gone bonkers. Kind of, I mean, I buy into the problem statement. I'm just trying to get a flavor of where we are in the adoption curve of what you're saying. Is it, is this the last 3 months? Is it the last 12 months? Has it been the last 3 years? Kind of.
For us, I mean, we develop the chips, so we talk to the cloud operators, and they give us pretty good roadmaps into where they see these challenges coming up. So for us, it's probably been close to 2 years, year and a half. We've known that some of this stuff was coming up and that things were changing. Now, nobody, including the cloud operators, knows for sure what the solution is. So now we're spreading out into the design space and trying to figure out what works. So everybody's in the experimental phase. We're all trying things. You'll see new congestion control algorithms being proposed by every different cloud operator. They're doing their own. You'll see traffic management, you'll see telemetry, brand new diagnostics. Everybody's kind of experimenting and trying to figure out where do we go from here and what's the best solution. So it's very early days. I think we're still in the experimental phase, but in order to do these experiments, my contention is that you need hooks. You need hooks in the hardware, right? You can't have some piece of software somewhere running in the NOC that's going to go out and do an SNMP get and just every 20 seconds pull in information. Way too slow. It's not going to work. This is real-time stuff that has to be optimized, and you need hardware to do it.
So just in plain English, for guys that don't design chips or do a lot of networking, line rate, please to explain.
Okay. So line rate just means that if the chip, for example, this TD5, it does 16 terabits per second total throughput.
Right.
You need to be able to do something essentially at 16 terabits per second.
Okay.
For every packet that comes in, I want to look at it, maybe do some diagnostics, do some kind of telemetry. So line rate means every single packet that comes in. I don't sample and say every 100th packet because my CPU can't keep up.
Gotcha.
I have to do it at line rate in the hardware.
Got it. Okay. Thank you.
All right.
Thanks.
Security, obviously another area, right? The attack surface is just getting bigger and bigger. And to be able to get fine-grained security control, again, requires looking at packets as they come in. You're going to look for a denial of service attack in a regular network. You need to look in real time and see this flood of packets coming in, tag it as behaving badly, and then do something with it. So all of these things kind of just get exacerbated as we move into the AI/ML.
It's interesting the thing you don't have on there, and you mentioned it a little bit around the heatsink. Are you seeing that you've got to do these things and keep the power consumption down?
Yes, that's right.
So you've got these two things pulling you from a tension point of view, but you can't just throw more performance at it and hang the consequences from a power draw point of view.
There are limits to how big a silicon die can be, the reticle limit. And when you hit that limit, you then go to chiplets. You have to split the chip into multiple pieces and then glue them together inside one of these packages. For power, you want to stay monolithic, which means one single die. So if you look at that TD5, there's only one die in there. It's a monolithic chip. It doesn't have chiplets in it. For power, that's what you want to do. Every time you add more chips, then you have to communicate between those chips and you're adding power.
Yeah.
So there's a constant trade-off between cost, silicon, die size, which affects the cost, power. This chip, as we'll get to in a minute, is in 5 nanometer. So we're using the latest of this stuff. But yeah, we're power constrained, we're cost constrained. So yeah. All of those dimensions we have to try and optimize over.
I have a question about the AI inferencing engine, but you're going to get to it later.
We'll have a few slides on that. That's brand new in Trident 5, so we'll get to that.
Thank you.
But as a preview, this is a fully programmable pipeline. So the entire packet processing pipeline is written in software in this language called NPL, Network Programming Language. And we compile it. You put in whatever you want. You want SRv6? OK, write some code for SRv6. Do you want some newer flavor of some kind of telemetry protocol? You write that in this NPL language, which looks kind of like C. You compile it, and it goes into the hardware of the chip and runs at line rate. Okay, so it's a fully programmable data pipeline. And off to the side, we have this inference engine, which kind of augments that regular packet processing pipeline. Remember, the packet processing pipeline we have in there has to be legacy compatible. So it has to do all of the things, all of the VXLAN, SRV, everything that our previous chips did, and in a similar way, so we can keep all the API compatibility, but we have to add functionality. And this NetGNT is sort of a thing on the side we'll discuss in a little bit.
Sounds like a lot of technical debt.
There's a lot going on. a lot of transistors in these chips. I think we're up to, what are we at? Close to 100 billion in the latest chips.
Can we go back to the programmatic pieces of it? So you said it's like a configuration language like C?
Actually, I'll talk to that in this.
Okay,
we got a little transition sluggishness here, but yeah, I'll get to that in.
It's not running at line speed.
No. Oh, now we've gone too far. See, now I'm out of sync. Okay. So this is Trident 16 terabit per second switch. So 16 terabits per second is coming in simultaneously and coming out. Just in terms of the math, sometimes you'll see some vendors say there are 32 terabits per second because they say take the input and the output and they add them together. We don't do that. It's just 16 terabits comes in. 16 terabits comes out as well, but you can handle the full 16 tera coming in. It has this 100 gig PAM4 SerDes. We discussed that previously. We do support 800 gig ports. So you're asking about Tomahawk 5. Yeah, that's our first generation to support 800 gig ports. This chip can now be plugged directly into the Tomahawk 5 via 800 gig ports. So that is the first time in Trident that we've been able to do that. We can also connect directly to servers, whether they're CPU servers, GPU servers, with 400 gig NICs. In the future, we're also compatible to 800 gig NICs, which are coming, and relatively soon.
Where are you seeing this now? You mentioned various things, 200, 400, 800.
Yeah.
Is it kind of equally split across all? Most of the action down at the smaller speed?
So for the,
Just
yeah.
contextualize that for me.
For the cloud operators, the big six, right, in China and the US, all of the game is at 400 and 800 right now.
They want to go as fast as
Everything. They're doing in-house NICs, so they're developing their own NICs that can do 400 and 800. Okay, so they're GPU servers, they use their own NICs, and they will connect directly at 400 straight into our devices.
Wow.
So the cloud operators are at 400 and 800. Our next generation will be 1.6 tera per port. The NICs will probably take a little while. The NICs always follow by about 2 years, roughly. And the cutting edge on the NICs is usually the in-house designs at the various Microsoft, Amazon. They all do their own.
they can just get them into
They design the NICs specifically for any of the funky stuff they want to do in their network. They put in special features in there, special sauce, so that they can do it on the NIC side of the network. And the idea is to make the rest of the switching network fairly generic. So their NIC does the special stuff, and the network itself can be simpler. Right?
And as soon as you bring out that 1.6 terabyte one, all of the demand's going to go there. So it's just the providers are hungry for whatever the fastest is.
The cloud providers will take whatever they can get. They're always going bigger and bigger and bigger. Now, it's an ecosystem. So we have the switch chips, but you need optics modules that plug into those things, and the cost and the power of those first samples are enormous. So typically what happens is we, Broadcom, and the switching group, we come out with our new switches. They support whatever, the 1.6T. It takes a little while for the optics ecosystem to come into play so that you can actually plug something in and use them. You know, we get early samples from vendors that are not really production ready, but we can test our chips. And then on the NIC side, usually it's either a commodity market, like we provide NICs, but the cloud operators also make their own NICs. And they tend to be.
So is that kind of a 12-month lag cycle in order to sort of get it in, do you think?
1 to 2 years, yeah,
Okay.
something like that.
That's interesting.
Yeah, until it goes really scale. So it usually takes, a year of initial development and testing and ecosystem, and the cloud operators take about a year to go into their labs and do small-scale trials of small clusters and make sure they've wrung out everything. Because when they light it up on production, they're lighting up, thousands of these things, and they cannot afford any downtime. They can't afford to roll back. No stoppages. So they test the living heck out of these things until they're sure it's 100% reliable before they go live.
They could be a year, 18 months in testing before they...
Easily.
Okay.
Okay. The SerDes in here is the same one we use in Tomahawk 5. You may hear this term linear optics or LPO. Basically, this is a lower power optics where because the SerDes, so you plug the optical module into a box. So the chip is driving a SerDes, and then the optical module has a SerDes and converts it into light. Okay. If you can drive a quality signal over that SerDes, then you don't need a lot of electronics in the optical module. Okay. And that's what this linear optics is. It removes chips from the optics module to make it cheaper and lower power. And so this is something that the Tomahawk 5 and the Trident 5 already support. And there's a separate standardization move afoot, a consortium that's doing this linearized optics, LPO. Okay, so the programming language, so the actual guts, this is a packet processing pipeline on the ingress, this is on the egress. There's obviously a lot of complexity that is hidden here, not shown, but it's all programmable. So we use this language called NPL. And you will probably be familiar with P4, the programming language for other chips. This is our version of P4. Why did we not use P4? That's a whole other story. Basically, P4 wouldn't do what we needed to do to make these power efficient, highly constant latency chips. P4 just wasn't designed to work with the kind of architecture we have in our chip. So many things it couldn't do, and to get P4 to do those things, in standardization, it would be too slow. So we actually use our own language, and we use this internally. So when we deliver a chip to our customers, most of them just take the NPL that we developed, we test it, we do all the software for it, and we ship it to them. Some customers do their own NPL.
Is that a language that's proprietary to Broadcom chips? Or is that...
No, it's open.
It's open.
Yeah,
okay.
It's open. Okay, so we're going to have to pick up the pace a little bit. NetGNT is kind of the big one. I'll talk about this. We do support some other new features. These things like cognitive routing was introduced in Tomahawk 5. This is the ability to do network level. So across many chips, you can figure out if I'm okay, there's a chip downstream from me that is congested. I want to avoid that one. So it's not just I know I locally am congested. You get a global system view of what's happening in the network, and you can make smarter decisions if you have a bigger view. There are some on-chip compute engines, these Cortex, and so you can also, in addition to programming the pipeline itself, you can write embedded firmware to go on these chips. And then the power here is about 350 watts. So all of this at 16 tera in the 5 nanometer process is coming in at 350 watts, and we're still managing to get the efficiency better with generation to generation. So compared to the Trident 4 generation, which was at 7 nanometer, we're 25% less power per port. Oh, and just briefly, that was the management port that we were talking about earlier. It's a 4 by 25 gig management port, and there's also PCIe for hooking up to a host CPU. And all of the buffering for this chip, the packet buffering, is on chip. There's nothing off chip. All right, so the kind of TOR box configurations. So this is a typical TOR with downlinks and uplinks. This configuration is kind of in the future when 800 gig NICs are available. Typically, it's going to be the in-house NICs developed by some of the cloud operators for their GPU servers. But 400 gigs all the way, NICs all the way down to 100 gig NICs. So you'll see boxes like this being developed by the OEMs, and it's the same chip inside all of these boxes, just how you configure the I/O on the chip. All right, so the key features at a high level, there's these 800 gig ports, the cognitive routing. We do have the on-chip, in addition to the pipeline being fully programmable, you can write these embedded firmware things. This is for things like 1588, BFD, anything that needs to sort of be at a management plane. It doesn't have to run at line rate, but it needs more flexibility. It's more than you can typically do in just a hardware pipeline. And then this NetGNT engine, which we'll get to in a second. All right, so NetGNT, this is new in Trident5-X12. And what it stands for, bit of a mouthful, so Networking General Purpose Neural Network Traffic Analyzer. Okay, so it's an inferencing engine that sits inside the chip, and it's in the Ingress pipeline. And its job is just to sit there and look at traffic patterns going through the chip. It's a neural network, and you train it to look for whatever you want it to look for. You want it to look for a denial of service attack, you have to train it how to look for that. You want it to look for some kind of security policy that's more than you could put in sort of simple tables, then you tell it what you want to look for, and it'll just sit there and it'll look at every packet that goes through and look at sort of trends in traffic patterns, and it will say, oh, I think I see this, and then it'll notify you. How training happens is separate. That happens offline. I'll show how that happens in a second. And yeah, so how it gets used isn't all that important.
Is the key takeaway there that it's at line rate?
It's at line rate, right.
So it's not sampling, as he's mentioned.
It's not
earlier.
sampling. You need to be able to look at every packet, and you need to be able to look at the full bandwidth of the chip. So this is the same kind of packet processing bus that we've had in all of our generations of chips. This is the new part. This is the NetGNT. It's a neural network engine. The number of nodes and neurons shown here is not to scale. But you can take, remember, this entire bus is programmable in NPL. And so you can do whatever you want here, and then you can extract information. And this can be any kind of information, timestamps, packets, inter-arrival times. You can feed it into this neural network, and it looks and it says, okay, I think I've detected a denial of service attack, if that's what it's been trained to look for. And then you can decide what to do. Well, just drop that flow. From now on, just drop the flow. That's the simplest thing. I could simultaneously say, start dropping that flow, and create a copy of the packet, send it off to the NOC, and say, hey, I just noticed that I think I'm seeing a denial of service attack, because the NOC may want to take global actions, right? Start looking for this particular flow with this signature across other ports, because if you're the first one to see it, everybody else is going to see it, right? It's a DOS attack. So you can take multiple actions. It's all programmable. And the key here is that all of this is line rate. There's no impact to the latency. So you'll hear some talk about run-to-completion models of programmability, which is like a piece of software. And if it's a complex packet processing operation, that run-to-completion can take a long time before that packet can go through. Sometimes it's short, but it's variable latency. This is all done in hardware. So it doesn't matter what you change in the programming. It doesn't matter what NetGNT is looking for. The latency through this chip is always the same. So you never have to worry about flows getting reordered or something, because some flows are slower than other ones. All of this is done in hardware at line rate.
I have two questions.
Yep.
So those arrows tell me, as the packet comes in, it gets passed through NetGNT, and then I'm guessing that means it comes back out and it's then labeled?
It's in parallel. So the packet goes down this pipeline. Yeah. And information from the packet is copied into NetGNT in parallel, looked at in parallel, and then resynchronized. So it comes out as the packet comes by here, then the output of NetGNT.
I was going to ask about the synchronization.
Right.
So so as that packet goes on, it knows to go and label that packet bad or good.
Yeah.
All right. So the next question. Is this a situation where NetGNT could, if you wanted it to, simply reroute that traffic or pass it somewhere else to like a digital twin? So if you knew it was a bad actor,
Yes.
that you could just say, go into this virtual reality and have all the fun you want.
Yeah, yeah, you could send it into a black hole. So you can change, the output here could be change my routing tables. So this flow that matches this signature, it keeps going, but it gets sent to somewhere else into a black hole, an analyzer, right? You can do whatever you want with it. You can change policies, you can block it, you can redirect it, you can make copies of it, you can sample it, whatever you want.
Send it to the FBI. Yeah.
That's right. Yep. Absolutely.
You're thinking of the NSA.
Oh, no, they already have.
Probably both of them. One copy to each. Okay, so I won't be able to do this a lot of justice with the time constraint, but we'll kind of go through it and you can ask me questions later. So how does training work? Well, how do you train a regular AI/ML? Well, if we want to identify cats, right? You get pictures of animals off the internet and some expert, in this case a human, tags a bunch of these and says, that's a cat, that's not a cat, right? And then you shove this into a training algorithm, and these are just off-the-shelf training algorithms from whoever, Google, Amazon, doesn't matter. And it comes out with inference engine rules if you know what you're running on. And now the inference engine in real time will look at pictures and say, yep, I think that's a cat. Okay, so that's how you train an AI/ML. In this case, what we're training this thing to do is look for traffic patterns. So the NOC gathers all these packet traces over weeks, months, whatever it is, and says, okay, on this date, we saw a denial of service. So they take a huge packet trace with good traffic and the denial of service when it happened. They send it to some expert. In this case, it's probably a network engineer, network architect, someone who can dig through like a detective and say, okay, I can see the signature of when this denial of service happened, and I can identify the characteristics, the signature, right? Was it the timing of the packets? Because nowadays they're randomized headers. Was it the timing? What characteristics would allow me as a human expert to say, ah, yeah, that's the denial of service? Tag all of that, and then the same thing, you just run it through this massive training algorithm. It spits out some weights, and then we load these weights into the chip, and then NetGNT will just sit there, and whatever the network operator taught me to do, I'll just sit there and I'll do it. Now, we as Broadcom don't define this. We provide the mechanism to get it into the chip. But the operator, whether it's Amazon or whoever, Microsoft, they have experts who say, okay, I will teach this thing what to look for. I'll decide, is it 95% accuracy? How willing am I to accept false positives? They handle the training. Then the training algorithm is off the shelf. You can get TensorFlow QAT as a quantization-aware training that you just get from Google, right? And you just run that with the training data, and it will spit out these weights, and then our API will load them into the chip.
So your solution sort of how far left does it go?
Our solution is this bit. We have the hardware in the chip, and we have APIs to, once these weights are available, to put them into the chip. The network operator, whoever it is responsible for all of this and generating those.
Do you see yourself coming further left down that stack, or is that you never go past that?
No, typically, I mean, there are very few people who can do this, who can identify, these kind of patterns. We certainly can't do that. Even at an operator, they have very specific engineers who would be able to do that.
Okay.
And it's a separate discipline to know how to run this thing. So it's probably two different engineers, one to set the training data, one to actually run this thing and decide when it's good enough. We will probably not, we have no plans to get involved in this part of it.
Okay. And if something goes wrong, they're responsible.
No.
So where does this training happen? This isn't in the chip.
No, this is in Azure, right?
Okay, so the training data needs to contain a good number of, we'll consider something bad happening a positive result.
Yeah.
You need to have those labels, and like you said, there's only a few people that can actually do that. But does that model, whatever you end up building, what you're training, how does it work on things that you haven't seen before?
It's just like any neural network. If you give it the right information and teach it properly, it'll
But
learn
if
how
you
to
don't
look
know what
for
to
it.
look for,
Well, we don't even define what to look for, right? We don't.
I get that you don't, but even through people that see, so it's still suspectable, suspect, I can't think of the word I want, to a new attack, right? If you don't know what to look for, you can't train the model, and there could be a new attack happening, and nobody would ever know. I'm not saying that's your fault or responsibility.
Right.
I'm just thinking about how the training actually happens.
Well, and you can train this to look for multiple things. So
I get it, but that's if you know what to look for.
right.
Right.
But if a human being cannot figure out what to look for, then the loop is open. there's somebody has to be able to figure out this is a bad thing, and I've got to figure out some kind of signature. Now, the tools to be able to figure out that signature depend on being able to capture this data at fine granularity on a packet basis with telemetry diagram, so that these are all hooks in the hardware that provide the tools to provide raw information back to somebody to try and figure out. We can measure things. We can measure queue occupancies. We can measure packet inter-arrival times. The chip is capable, has the hardware to provide lots and lots of raw information. Now, somebody has to digest that and then say, how do I turn that into actionable training that I can get? And that part is going to take a while. Absolutely. This is a new tool, and we're going to be working with the operators to figure out how it gets used.
Right. It's a new feature.
Yep.
And my next question was going to be, how often are you updating the inference? And that's not on you. That's on the operators.
Yeah, they can update. This can happen in operation. You can update to a new training inference, new inference on the fly while the system's running.
Yeah, because deploying the model shouldn't take that long.
Right.
But the training could. I mean, we're talking, you're going to have to go through.
Could be weeks. Could be weeks.
I don't know
or
how
months.
much data you would really need, but you need a sizable amount and a lot of positive results in order to distinguish what's good and bad.
Right.
It almost sounds like kind of like currently right now, day to day, say you get a DDoS attack or whatever, we have to go through, okay, let's figure out the patterns, and then we're going to train this. And I guess the goal is to help so that when we figure out a pattern, we can use this, put it in like some of our other equipment, and it will help us catch things. I guess another thing too is like, is there any kind of plans where, as say these things get trained, would that be shared? So then that way.
Right, and that's up to the operator if they want to share that information, best practices, they can do that. You can use the output of the chip as a feedback information to a higher level training. Like, you can do some sampling or set the threshold really low so you get a lot of false positives. Don't do anything. Just let the traffic keep going. Trap those things, feed them up to some higher level AI where they filter it out and say, okay, I'm going to try and so it can be at multiple levels, and it's kind of TBD. You can use it as raw information. Really, these are hooks and these are tools that provide information that hopefully can become actionable, and you can get the chip to do this in real time.
Okay, yeah, because I'm trying to figure out like, how would it make my life easier today from what I'm already doing, I guess, because now it's like, I'm going to still have to go chase this down, get the info, and then train the chip. And so now it's almost like, is my work getting doubled? But is it because like over time, it's somehow going to make my life easier?
Well, the goal would be once you've trained it the first time, it'll sit there, and the next time a DDoS comes up, it's autonomous. It squelches the whole thing. It lets you know, oh yeah, it happened, but I took care of it.
Okay.
Okay.
I guess I'm also thinking about, because like say like some things I use now is like I'll use like a CDN. And so I'll use that to kind of go, hey, here's this signature, this pattern that keeps happening, and then I just block it at the CDN level. So I guess I'm trying to just understand like.
Yeah, and you can get it to look for those signatures and let you know, right?
Okay.
So in real time, the network is smart enough to be looking for whatever you want it to look for. Because you as a human can't look at all the packets in real time.
No.
So you get this thing to look in real time and give you some hints or hopefully better over time, better and better answers, more accurate answers. But filter it, right? So filter it so that it's actionable, useful information to you, and then you can decide how to push that back into actions for the network to take. Yeah.
So again, a DDoS attack, right, on say Amazon on Prime Day is very different than somebody trying to sneak under the radar and slip something into the network that's going to sit out for months.
Right.
We hear about this happening all the time.
Yeah.
So the ability that if that, like you mentioned, right, Shala, that it was a different pattern that was already known by a security service or whatever, that
Yeah.
they could possibly send that over to you and go, hey, because you've got this chipset, you can make this happen.
It's almost like
I
me, if I oversimplified it, if I think about, say, like Norton or something like that, we all kind of like send that info. And
Right.
so over time it gets shared across. So it's just like, oh, I found out about this happening here. And so that way it helps everybody, like globally.
Yeah.
So I guess for me, that's what would be like super interesting, because that would make my day-to-day easier.
Right. And, you know, eventually, who knows, you can get the industry coming together and saying, hey, we're all facing the same problem, let's share best solutions. You could get regulators coming in and saying, you have to take action on certain things, and you have to keep logs of these things, and you got to share them. Whatever it is, this thing can do it, but the important thing is you have to be able to do it in the network.
Sorry, one question. So the model, it's uploaded by operator, right?
Mm-hmm.
It's uploaded on the firmware level, right?
Yeah, it's actually loaded into the hardware.
In the hardware. So when you train your model and add to this configuration file, right? And you put it on the chip, how easy is to change the version for the new one? Because usually the model's, you know, evolving, right?
Mm-hmm.
So you have a fleet of switches everywhere, for example, and you want to just update through you do it with the API, or you do it by firmware update. How you upload the new version of model?
Yeah, you can do like a warm boot or an ISSU and push this out, because so this piece of the chip can be entirely turned off. The NetGNT, you know, by default, you can just turn this whole thing off and so you can turn it off, load it on the side, in parallel across all the chips in your entire network, and then turn them all back on.
But to turn them back on, I need to change firmware, or just I'm doing it through the API?
No, you just send through the API, and in real time, it'll just turn it on while the packets are still going.
Thank you. Thank you for the information.